Hi, so in this video, what we're going to be doing is we're going to be taking a linear transformation from some space into some other space, and we're going to, in this video, look at what the image of that transformation looks like. In the subsequent videos, we're going to take a look at the kernel, the rank, the nullity, and how to put all of those things together. And so the first thing we want to observe is that the input to t here is a four-dimensional vector, right? X, Y, Z, W, and the vectors that take on that form have four dimensions, and its output is a three-dimensional vector, right? It has 1, 2, 3 entries here. But do note that just because the outputs are three-dimensional vectors doesn't mean that the image of this transformation necessarily has to be a three-dimensional space. You could take the whole four-dimensional space and flatten it down to a single point, or to a line, or to a plane, or maybe to the entire three-dimensional space. We don't know. Let's write down what we do know. We know that that t is a transformation from R4 to R3, and the question for this particular video is, what is the image of t? And so the first thing we want to do is to find the standard matrix of t as a transformation. So if we imagine the columns of the matrix as being actions on x, y, z, and w respectively, then your sort of standard matrix is called M, is going to be 1, 0, 1, 2, 0, 2, 3, 0, 3, and minus 5, 1, minus 5. Alright. And if you recall what the columns of the standard matrix do from the activities from this week, we know that, say, what this is telling you is that t of your standard basis gives you the columns. So t of 1, 0, 0, 0 is going to be 1, 0, 1. And t of 0, 1, 0, 0 is going to be 2, 0, 2. T of 0, 0, 1, 0 is going to be 3, 0, 3. And finally, t of 0, 0, 0, 1 is going to be minus 5, 1, minus 5. Alright. So what this is telling us is that the image of t, right, the domain R4 is made up all the different ways that you could take linear combinations of these four vectors, right? The four standard basis vectors. Every single four-dimensional vector looks like something like this. So what's happening now is, having applied the transformation, the image of t is going to be all the possible linear combinations, or the span of the images of these vectors. So the image of t is going to be the span of the set 1, 0, 1, 2, 0, 2, 3, 0, 3, and minus 5, 1, minus 5. But you could probably already see, even briefly, visually, that we're not looking at four linearly independent vectors here, are we? First of all, that's not even possible because this is a three-dimensional space, so the maximum size a set of linear independent vectors could have is 3. But also, we can easily see, for example, that 2, 0, 2 is a multiple of 1, 0, 1. So if I wanted to see, if I wanted to find, say, a minimal spanning set or basis for this span, what I need to do is go back and recall what we've done in the past to find a basis. So I'm going to go ahead and make a new matrix here that I'm going to call, well, it's not letting me change the name, and that's fine. So we're looking at 3 rows and 4 columns, 1, 0, 1, 2, 0, 2, 3, 0, 3, and minus 5, 1, minus 5. And if I take that and I find this reduced row echelon form, we'll note that the pivots occur in the first and last columns. So what that is telling me is that the first and last vector of this matrix, or the first and last columns of this matrix, correspond to the vectors which form a basis for this space, or a basis. So the span of that is also equal to the span of just 1, 0, 1 and minus 5, 1, minus 5. So that is the image of T. And we'll note, since that's the basis and the basis has 2 elements, the dimension of the image of T is 2. Just as a fun fact. So what that's telling us is that this 4-dimensional space through T has been smushed down to a 2-dimensional figure. Alright, thank you very much. I will see you in the next video.